So, good evening, everyone. Welcome to the second live class of the course Industrial Wastewater Treatment CE40. I'm Niketa. I'm a PhD student at IIT Madras and I'm also a PMRF scholar. So, I will be the TA for all the live classes. So, I hope you have watched all the lectures in the second week. So, do you have any questions? So if there are no questions, then we will proceed with the class. So what I will do is I'll give you a brief of the topics that you've covered in the second week's lectures, and then we'll have a question and answer session. Okay. So the first topic today will be ion exchange. So can someone describe what ion exchange process is? What happens in this and where is it used? So this process is mainly applicable for hard water. And what causes hardness of water? Hardness of water is caused by ions of calcium and magnesium. And in order to remove these ions, we can use ion exchange process. So ion exchange is, as the word suggests, it's an exchange of ions. So the ions in the water or wastewater are exchanged with the ions in the exchange membrane. So water, if there is a membrane here, water is passed through the membrane, and as the water passes through, whatever ions are present here, they get exchanged with the ions in the membrane. So usually the ions in the membrane are sodium, and these this is about a cation exchange membrane. So anion exchange membrane also has the same process but with the anions instead. So here the whatever calcium ions are there, they get exchanged with sodium, and then the outlet will have sodium ions instead. So whatever the calcium and magnesium ions are there, they get attached to the membrane instead. And after a while, we have to regenerate the membrane. So that is done by passing a solution of brine. So brine usually means a concentrated solution of sodium chloride. So the sodium in the brine solution will again come back to the membrane in this regeneration process. So this is done in batch as well as continuous mode. So can someone give me the difference between the two, batch and continuous, what it means? Are there any chemical engineers here?
Continuous process is basically like organic process, and batch process is for uh, industrial water like ETP, which can take batch as a SBR, sequential batch reactor. We can be using UASB
Right.
anaerobic sludge bank.
Okay, so UASB and SBR are based on the batch process. But
Yeah.
my question was, what is the difference between a batch and a continuous operation mode? What is the basic
Uh,
difference between the two type of processes?
in continuous process, there is a aeration tank which feeds some culture and it goes to the return sludge, which can continuously perform in water. And in batch process, there is a filter water as a batch wise.
So, the difference between a batch and a continuous mode of operation is, in batch we have a small, as the name suggests, this means we take a small batch of the wastewater in a container and then we treat it and then we let it out. Okay, and once we let it out, the tank becomes empty, and then we send a new batch of wastewater that needs to be treated inside. So that's what happens. So in a batch reactor, the water or wastewater is treated in batches. Whereas in a continuous mode, what we do is we continuously supply the wastewater, and here we have a stirrer. So the stirrer keeps rotating, and then the reaction happens, and then continuously the water is also being sent out. So, like Sagar suggested, the very good example will be an aeration tank. So here, continuously we are letting the wastewater inside, and the biological process happens, and it is also being stirred and aerated regularly. And after treatment, the wastewater is also being let out continuously. So this kind of a process is called continuous, and this is a batch process. So there are these two modes of operating ion exchange process. So in a batch ion exchange process, what happens is we take a small, not a small volume, a fixed volume of wastewater that needs to be treated, and then we add the resin or the uh, membrane that needs to exchange ions with the ions present in the wastewater, and then it is continuously stirred. So, what happens when stirring takes place is that whatever ions are present here will get exchanged with the ions in the water. So, this is a batch ion exchange process, and in a continuous process, like I have shown here, continuously ions will be coming in, continuously the wastewater will be coming in and getting exchanged, and then there is a continuous outflow also. So, there is a continuous inflow and continuous outflow. So after after the resin's capacity is reached, that means there are no more sodium ions present for exchanging. At that time, the regeneration happens, like I said, using a brine solution. Okay, so now we'll come to different types of resins. So the first one is strong acid cation exchange resin. So, as the name suggests, it. This is highly ionized. And usually it is made using strong acids, so that is why the name is called strong acid cation exchange resin, and it can be operated over a large pH range. And the second one is the weak acid cation exchange resin. So here, mostly it is having carboxylic acid group. So that is why the name is weak acid cation exchange resin. And the pH range for operating is also short. And mostly it doesn't work in acidic pH. Now coming to anion exchange membranes. Again, just like strong acid, we also have a strong base anion exchange resin. So this is also highly ionized. And long pH range. And then last is weak base anion exchange resin. So this has a low ionization capacity. And also it is not effective at alkaline pH. And then we also have special resins for removing heavy metals. So those are selective to heavy metals. Okay, so now we'll go to properties of ion exchange resins. The first one is the exchange capacity. So what is exchange capacity? What is exchange capacity of a resin?
Specific volume of a resin that can exchange
Yeah.
anions or cations is called capacity of that exchange resins.
Yeah, so it is the amount of ions that can be taken up by a given volume of the resin. So that is expressed in equivalent weight per liter. And then the second property is particle size. So why particle size matters? Because if there is uh, less size, then the flow is also, less size means more surface area. So compared to bigger particles, smaller particles have the advantage here because they have a larger surface area. So that means there will be a better ionization happening. So ionization efficiency will be higher if we use smaller size particles. But the problem with small size particles is the more smaller the particles become, the smaller the pore size also becomes. So if you have very small particles, then the pore size will also reduce compared to bigger particles. So that will be a problem. So what happens if there is a reduced pore size is the water will not be able to flow through. So if you have a membrane like this and water is coming through, from the top, and the particle size are tightly packed here, and the particle size is very small. So, which means the pore size is also small. So then, what happens is the flow will become restricted. So we need to apply more force in order to make the water flow through. So that is an issue. And then there is stability. Yeah.
Ma'am, ma'am, if the particle size is coarse, then which type of resin is used?
We just saw the different types of resins. So all of this can have big or small particle size. Particle size is independent of the type of resin.
Okay.
So material can be anything, but like we are just seeing what how particle size will matter. So no matter what kind of material we are choosing as resin, we should ensure that the particles are not very small. If that is the case, then there will be flow problems.
So, ma'am, if the particle size is more, then the less surface area will be conducted.
Yes. So we need to find a balance between both. If we think that less particles means less flow, so we go for bigger particles. Then if we go for very big particles, of course there will be reaction will not be so efficient. So we have to find a balance between both.
Okay, ma'am.
So generally what happens is that when we pass water through a membrane, it will tend to swell a little. I mean, there will be certain kind of swelling that happens because it's a resin, so it can trap water and there will be some swelling. So after a while, it will come back to its original size. So this shrinking and swelling, it can damage the membrane over time. Because it is expanding and it is reducing. So that means some bonds will be broken in the process, some chemical bonds may be broken. So when that happens in repeated cycles, the life of the membrane is going to reduce. So this thing is called stability. Stability means like how resistant a membrane is to continuous swelling and shrinking. So if a membrane has low stability, it means it is not very resistant to shrinking and swelling. Okay, so now we will see exchange capacity in detail. So there are two types of exchange capacity. The first one is total exchange capacity. And the second one is operating capacity. So can someone tell me the difference between these two?
Total number of
Ma'am, can I?
Anyone?
Ma'am, in total exchange capacity, the total ions will be exchanged, and in operating capacity, some particular ions are exchanged.
Mm, okay, some other answers?
total exchange capacity is the capacity of the resin for a unit volume. But operating capacity is the useful volume which can be exchanged. That is the difference.
Okay, so total exchange capacity means until all of the resin is exhausted. So until we reach 100% exhaustion, that capacity is called total exchange capacity. So suppose we have given amount of sodium ions. So until we reach the stage where there are zero amount of sodium ions present in the resin, so that is the total exchange capacity. That means there are no more ions left in the resin for exchange. Whereas operating capacity means we fix the limit. We are fixing the limit. Like for example, if we say that okay, until we get 80% exchange is enough, so then we stop the process at 80%. So that is the operating capacity. So this operating capacity is more commonly used because like that is more practical. We don't generally go for the 100% exchange capacity. We fix like we want only this much, and then we design accordingly. And then there is breakpoint. So breakpoint means is what breakpoint means is that generally in ion exchange there will be an inlet and then there is an outlet. Okay. So this is the inlet and this is the outlet. So inlet, let's assume that the concentration of the I'm just giving an example here. So if we assume that we have calcium and magnesium ions and we assume their concentration is 100% in the inlet, once the exchange happens, their concentration will, I mean, we are just assuming here that it should reduce to about 10%. So what happens in breakpoint is that after a certain stage of using the same resin over and over again, this concentration will slightly increase. So maybe it will become 60% or 70%. So this increased concentration will not be, will not be according to the norms. So we have some standards, right? Standards for wastewater disposal, standards for water, drinking water, etc. So if the outlet concentration is high enough that it does not meet the standards, then we call that point where the concentration exceeds the required concentration. That point is called breaking point. So this breaking point is measured in terms of time. So it could, time and as well as volume. So it could come after 2 days, after 3 days, sometimes after weeks, sometimes in hours. Depends on various factors. So breakpoint is where your outlet concentration is exceeding the limits laid down. So if it is very high than the discharge limits, then if it is going to be if the outlet concentration is higher than the limits, then that point is called breakpoint.
Ma'am,
Yeah.
ma'am, after the exceeding the resin, then after it will be exhausted. Then if there is a limit of the exhaustion after breakpoint.
Yeah, there will be. Breakpoint is not the breakpoint does not mean the ion exchange membrane is exhausted. That just means the outlet concentration of ions is very high. Still there is exchange happening. Exchange capacity will reduce, but exchange amount of ions exchanged is less, but still there is exchange happening. That's the difference between the two capacities. So total exchange capacity means 100% of whatever ions were there on the resin are exchanged. But and then I'm sorry, I'm confusing. So breakpoint means the amount of time that it takes so that the concentration that is exiting the membrane will be higher than the norms laid down. So this, if it continues further, if the process is continuing after this, then there will be 100% exhaustion. At breakpoint, there is not 100% exhaustion.
Ma'am, though in exhaustion point, if the ions will be exchanged or not?
Exhaustion point, no, because whatever ions were there on the resin are exchanged now. So there are no more ions left for exchanging. So that is why we call it as exhaustion point.
Ma'am, so in exhaustion, it will be incinerate?
After exhaustion, you mean?
Okay.
No, I'm asking you, like, what is your question? You're asking incineration.
Ma'am, I am telling that you have told that there is a break point. In that, after the certain temperature increases, the exchange of ions will take in the exhaustion point, right?
I never talked about temperature.
Okay. Okay. After that, the ions will exhaust, and that point is known as exhaustion. Is there is a limit that the certain in that?
Yeah, that's what I'm saying. Breakpoint can happen at any time. Like even if the resin is not completely exhausted, breakpoint can happen. Breakpoint simply means the outlet concentration of ions is high enough that it is not acceptable. Suppose we want 0% ions in the outlet, we are still getting maybe 10 ppm or 20 ppm ions in the outlet. So that is not acceptable, right? That means the solution, whatever is entering, it is not getting 100% exchange. Some of it is coming out. So that point where the resin starts giving ions in the exit solution also, then that is breaking point.
Okay, ma'am.
Okay, and then we come to regeneration. We've already discussed this. Regeneration means restoring the capacity of the ion exchange membrane, and that is by passing a solution of brine. And in order to find out which kind of ions will be getting exchanged in the membrane, we can do that by using the selectivity series. So selectivity series is like a series which tells you how much the affinity for the between the ion and the membrane is. So higher the affinity, more likely is that the ion will get exchanged by the membrane. So that is the selectivity series. And then we have the regeneration efficiency. So this is the total equivalent of ions removed from the resin compared to the total equivalent used in the regenerant. So what this means is, like, if we are using a regeneration solution and the ion that we are regenerating is sodium, so the regeneration solution will have 100% of sodium ions. So when that is used for regenerating, what will happen after the water passes through the membrane is there is exchange happening. So from 100%, the ions concentration in the So the concentration of the sodium ions in the resin is going to reduce. So it will drop to maybe about 90% or 80%. And the rest of it will be removed. So removed and it will be going out with the water. So regeneration efficiency is the total amount of ions that is removed from the resin. In this case, it will be if it is 90%, then it is 10% of the sodium ions will be removed. So along with the water that is coming out, 10% of the sodium ions will come, and the remaining will be present inside the resin itself. So after giving 100% of sodium ions in the regeneration in the brine solution, 10% of it is coming out along with the effluent. So this ratio of ions that are removed from the resin to that which was used in the regeneration solution is your regeneration efficiency. So now let's look at the type of regeneration system. The first one is co-current. The second one is counter current. So can you tell me the difference between the co-current and counter current? What is co-current flow and what is counter current flow?
Ma'am, in co-current flow, the resin will be in the same direction, and in counter current flow, the resin will be in opposite direction.
One second. Someone tried to.
In co-current operation, the service flow in the downward flow, and in counter current there is reverse generation flow, which is service flow is in
Some technical issue.
upward flow.
Is my screen visible? Okay. So yeah, counter current and co-current. So this means co-current means the both the flows are happening in the same direction. That is, the regeneration and the inlet are in the same direction.
Madam, your voice is not coming.
Voice is not coming. Oh. Am I audible now?
Yes, ma'am.
Yes,
Okay, thanks. Okay, so we were just discussing about co-current flow. So imagine this is your resin, and the water or the wastewater that needs to be treated is coming from the top down. So this is the general direction of the wastewater flow inside the resin. But we want to regenerate now, and then for that we are again using the same direction for passing the brine solution through the resin. So then it is called co-current flow, where the direction of the regeneration solution and the direction of the wastewater is the same. So then it is co-current flow. And then counter current means the resin is like this. This is the direction of the wastewater flow from top down. But instead of co-current, we are going to pass the solution from in the opposite direction. So from down, it is going to come up and pass out. So then this is called counter current flow. So, can you tell me which of these will have a better efficiency?
Counter current, ma'am.
Yeah, because since we are moving in the opposite direction, in case there are any blockages or anything, all of that will get cleared up. And it also ensures better efficiency also. So efficiency is higher in case of counter current flow. Okay, next we come to applications of ion exchange. So can you list out the applications where ion exchange can be used? One example we have already seen for hardness, but in other industrial settings, what other applications are possible?
Removal of heavy metals.
Yes.
Is using as ion exchange.
And then in case we have ammonium or nitrate, all these ions in the water or wastewater, that can also be removed. So nitrogen control, mainly for ammonium and nitrate. Then for water softening. So for the nitrogen control, we prefer natural zeolites because it has a higher affinity to ammonium ions. And it can be regenerated by adding lime. And if there are any ammonium ions present in the resin, those will be converted to ammonia gas. And the gas is removed by air stripping. So air stripping we will be seeing in the next week's lectures. And again, backwashing is also done. So can someone explain what is backwashing? It is closely related to counter current flow that we just saw.
Backwashing means rinsing of the filter or any membrane, which can
Yeah.
be used in house.
But how does it happen? Like, what is the how is the flow given?
If flow is given by upward to downward, so backwash is given by downward to the upward.
Yeah,
So it
in the
can
opposite
be
direction. So
yes.
that whatever, if there are any impurities or dirt which is blocking the pores, they can get rinsed off. So here, in nitrogen control, we use backwashing with to remove calcium carbonate. So usually in this process, because the regenerant is lime, so there will be formation of calcium carbonate in the between the pores. So we have to remove this, otherwise it will lead to pore blockage. So we need to backwash regularly so that the calcium carbonate solids are removed. And then it is also used for water demineralization. So demineralization means removing whatever ions are there in water. So that is how we get mineral water, is by demineralizing it. So here for this, since it requires removing all ions, so we need to apply both anion and cation exchange. So since we have to remove all ions, we have to do anion exchange plus cation exchange, one followed by the other. And then we'll come to heavy metal removal. So why should we remove heavy metals? Why should we remove heavy metals?
It can be block membrane. That's why we have to remove heavy metals.
Any other answers? What happens if we drink water with heavy metals? Yeah, so heavy metals are highly toxic in nature, especially chromium, etc. All of these are carcinogenic. So chromium, mercury, lead, yeah. So all of these are carcinogens. So that is why it is important to remove all these heavy metals in water. And also another reason can be that if it is possible to remove these heavy metals and recover them, then we don't have to buy them again and again. So if we can just recover it from the wastewater, we can use it again for the process instead of buying a fresh stock. So for it is required because it is toxic and also for metal recovery. So before we pass water through a resin, it is very important that we treat it. Treatment means removing any suspended solids. If these solids are not removed, what will happen is it will go and sit near the pores and it will clog the pores. So in order to avoid that, we have to remove all the suspended solids before passing through the resin. So that's why we need some kind of pre-treatment or filtration is required. And sometimes if the water or wastewater has a high amount of organics, then we need to use solvents like methanol because they can bind to resin and reduce its capacity. Or we can also use resins which can scavenge the organic ions from the water or wastewater, so that the main resin which is used for the exchange will not be affected by the organics. So in order to find the exchange capacity of a resin, we need to find out C by C naught ratio. So what this ratio means is if your inlet concentration of the ions is C naught and the concentration of the ions at any point in time or simply C, what this means is this is the outlet concentration of the ion at any point in time. So we can use a calculation of C by C naught versus time to determine the exact weight and the volume of the resin which is required for a given volume of wastewater. And then we have breakthrough curves. So breakthrough curves will tell us at where the breakthrough point is coming, and based on that we can design the resin. And based on that we can calculate how much volume of resin will be required, and for treating how much volume of wastewater. Okay, now we come to adsorption. So what is adsorption? What is adsorption?
Adsorption is a surface phenomenon.
Yeah. So adsorption is a surface phenomena, and what this means is that uh, if we pass a solution having a certain pollutant through an adsorbent, it won't. The pollutant will not go into the bulk of the adsorbent or bulk of the material. Instead, it will be binding to the surface alone. So this is absorption. And here there are two terms. The first one is adsorbate. So adsorbate is the substance that gets adsorbed, and then adsorbent is the substance which is adsorbing. So the material which is binding, like for example, you have activated carbon, all of these are examples of adsorbents. And adsorbate is the substance which gets bound to the adsorbent. So adsorbent is temperature dependent. So there are two kinds of adsorption processes. The first one is endothermic, meaning it takes up heat, and exothermic means it gives up heat. So physis option is endothermic. We'll see what this is. And chemis option is exothermic. So physis option means that the adsorption process is only through physical bonds, like maybe van der Waals forces, or some weak attractive energy which keeps the bond together, and it is highly physical. So physis option is easily reversible. So we can just apply some heat or add some solvent. So if we do any of these processes, then the adsorbate will come out of the adsorbent easily. But that's not the case with chemis option. So in chemis option, the bonds are more permanent. And these are formed by chemical reactions, so they are also called chemical bonds. And these are not reversible. So once something gets chemisorbed, it is going to stay that way. It's not possible to recover it or remove the substance from the adsorbent. So the main driving factor of adsorption is the surface energy. So the surface energy is what decides whether the substance will get adsorbed or will not get adsorbed. Now coming to the mechanism of adsorption. First, we have bulk solution transport. So, when we talk about how adsorption happens, first it will have to transport. So, first it will have to travel, and there is transport of the substance inside. On the surface of the on the surface of the adsorbent. And once the transport process is over, the final one is the adsorption process. So, adsorption is the last one. The first three stages are all about how the substance is transported. So, first one is bulk solution transport. So here, for bulk solution transport, we assume that the concentration in the liquid is uniform. So whatever material is supposed to be adsorbed, the adsorbate, we assume that the concentration of the adsorbate is uniform in the liquid. So if you, for example, if you have some organic matter that needs to get removed, so we assume that first the concentration of the organic chemical is uniform in the wastewater, and then the adsorption and the transport of the chemical is driven by advection or convection. So first we have to have a uniform concentration of the solution. For example, let's assume that we have some organic matter in the wastewater, and the wastewater is it's in a container and it is being transported to an adsorbent column, and it is passed from top down. So first we have to assume that the concentration of the organic chemical is uniform throughout the liquid. So now in that case the adsorption will be driven by advection and convection. So advection means using some kind of a force, like it could be using some kind of velocity. So what this means is we need some pushing action for the liquid, and then the contaminant will come in contact with the adsorbent. So we just have to maintain some flow or some velocity, some force in order for the contaminant or the adsorbate to come in contact with the adsorbent. And convection is again because of temperature difference. And the second transport is film diffusion transport. So for bulk solution transport, another example would be river water. So in river water, we assume that some of the sediments at the bottom of the river are good adsorbents, and if we assume there is some organic contaminant which is flowing through the river, then it is quite possible that the advection or the continuous movement of the river will make the adsorbent come in contact with the sediments. So, sorry, it will make the contaminants come in contact with the adsorbent. So, the first one, the first stage is more about the process being driven by velocity or some kind of an external force. And then we have the film diffusion transport. So here it is the adsorption, I mean, the transport is driven by a concentration gradient. So what this means is when we put the adsorbent inside the solution having some contaminant, then, for example, this is activated carbon. So this is a solid particle inside the liquid, right? So once inside, it will form a film. Okay. So this liquid film, inside the liquid film, there will be different, there will be some kind of a partition. So here, this portion is called the bulk liquid, where the concentration of the pollutant is uniform. So I'm just going to expand this section here. This is the activated carbon particle, and this is your film. And outside the film is all bulk liquid, and here the concentration of the pollutant is going to be uniform. But at the interface here, so at the film here, the concentration inside the film is going to be slightly lesser than the concentration outside the film. So this creates an interface, and this creates a concentration difference between the inside and the outside of the film. So let's assume that there are two different concentrations, C1 and C2. So the concentration of the pollutant is higher outside. So C2 is going to be higher than C1. So because there is a concentration difference, there is going to be a gradient, and because of the gradient difference, more liquid from the outside, more contaminant or more adsorbate from the outside is going to come inside. Because what concentration gradient does is it tries to balance the concentration on both sides. So wherever the concentration is more, from there, the liquid or the pollutant or the adsorbent will come to the place where concentration is less in order to balance the concentrations on both sides. So this happens. So because of this movement is driven, so because of this adsorbate from the bulk liquid will enter the film and it will get adsorbed onto the solid here. So this is the film diffusion transport, which means that because of the concentration gradient, the adsorbate is getting transported near the surface of the adsorbent. And then we have pore diffusion transport. This is the final stage of transport. So this is also driven by concentration gradient, but here the concentration gradient is not between the film and the bulk liquid. Instead, it happens on the surface of the pore. So imagine that this is your activated carbon, and what I'm drawing is a structure of a pore. So this is going to be your pore. This yeah. So here also there is going to be a concentration gradient, because now that the pollutant or the adsorbate is already at the surface and it has some given concentration, say C, say C1. So compared to the compared to the concentration of the pollutant at the surface of the pore, the concentration inside the pore, which is in this place. So here there is no pollutant, right? So here the concentration of the pollutant is almost negligible. So because of that, there is a concentration gradient which is happening. So outside the surface of the pore, we have a high concentration of the adsorbate, and inside the pore surface, there is negligible concentration. So here, your concentration inside is less than the concentration outside. So because of that, there is a concentration gradient. And like in the previous case, because of the concentration difference, the both the concentrations try to become equal, and because of that, more of the adsorbate from outside will start coming in and settling at the pore. And then the final step is adsorption itself. So now that the adsorbate has come inside the pore, the final step is forming bonds. So it could be either physisorption or it could be chemisorption. So for physisorption, like I had mentioned, it is an endothermic process, so there is no energy required. There is no activation energy required. Whereas for chemisorption, we need a high activation energy. So this results in the formation of a different compound also. So because there is a chemical reaction happening between the adsorbate and adsorbent. So there is a chemical reaction which is happening between the two, and then this will result in the formation of some new chemical compounds. Okay, so now I have a question. What is the most commonly used adsorbent material?
Activated charcoal.
Activated carbon, yes. So how is it produced?
Bone char also.
Yeah, any kind of char. So char needs to be activated. So producing activated carbon is a two-step process. First, we have to produce char. So in order to produce char, we have to heat any organic substance, like it can be bones, it can be plants, it can be animals, it can be anything organic which will have a high carbon content. So we can just take it and heat it at 700 degrees Celsius in the absence of oxygen. So this will produce a highly porous substance called char. But just char will not be enough. So it is porous but not as porous as activated carbon. So in order to convert char into activated carbon, we have to do an activation step. And activation is just heating the char at higher temperature. So first we heated at 700, right? So now we will be heating at 800 to 900 degrees Celsius. And we will be activating it by passing a stream of steam or carbon dioxide gas. So if we do this, then the pore structures are even more will be increasing, and they will have a highly porous surface. So this process is called activation. So producing activated carbon is a two-step process. First, we have to produce the char by heating in the absence of oxygen at 700 degrees, and then we have to activate it by passing steam or CO2 at 800 to 900 degrees Celsius. Okay, so now let's come to
Madam, one question.
yeah.
Passing CO2 or steam at 800 to 900, you told no, madam.
Yes.
But at that temperature, that carbon dioxide will not be stable, no, madam. It will be converted into
Yeah,
carbon.
yeah. So this is following. After heating at 800, Then it will be passed with steam or CO2.
Okay, ma'am. Okay.
Yeah.
Thank you, ma'am.
Okay. And now coming to pore classification. So here we are going to classify the different types of pores on activated carbon. First one being macropores. What are macropores?
Diameter of the pore is more than 50 nanometers. That is macropore.
Yeah, more than 50 nanometers. And then mesopores. What is the size of these pores?
2 to 15 nanometers. 2 to 15 nanometers in between.
Yeah, so 2 to 50 nanometers. And then micropores,
Anything less than 2 nanometers diameter.
less than 2 nanometers.
Yes, ma'am.
So then we have different types of activated carbon. The first type of activated carbon is granulated activated carbon. And the second one is powdered activated carbon. So the difference between these two is the size. Granulated activated carbon will exist as granules, like approximately like about 2 to 5 in diameter. So these will exist as granules, and these are like generally used in water filters. And then we have powdered activated carbon. So these are just the same substance, but it is ground finely and it is made into a powder. So powdered activated carbon is just like a powder. So this is used for gases mostly because it has a higher surface area. And yeah, then coming to factors affecting absorption. The first one is solubility. So, why solubility matters is if a substance is highly soluble in water, then it is not very absorbable. But if a substance is less soluble, then it can be absorbed easily. So, for example, we have an mixture of water and oil. If we try to absorb the oil from water, or if we have grease or something, then absorbing that oil or grease is very easy compared to absorbing some dissolved organic, because already it is not attached to water, so it will easily stick to the surface of the adsorbent. So that is why substances which are highly soluble are slightly more difficult to absorb. And then the second factor is temperature. So when the temperature is high, your physisorption will be less. So physisorption is highly temperature dependent. In at very high temperatures, physisorption capacity reduces. So physisorption at high temperatures is the efficiency will be very low. And then pressure. So physisorption especially is pressure dependent. If we increase the pressure, then the physisorption process also increases. And in terms of and for chemisorption and temperature, chemisorption will increase as long as we reach a equilibrium temperature. So once we reach that, it won't increase. And then we have adsorption isotherms. So isotherms are generally plots which are which are plots which are made assuming that the temperature is constant. So we have different types of mathematical equations or mathematical models where we assume the temperature is constant and which can represent the adsorption process effectively. So in order to find out how much adsorbent will be required for a particular type of adsorbate, we need all these isotherm plots. So these are mathematical models basically. So depending on the type of adsorption, we have different models. So if the process is reversible, the adsorption is reversible like physisorption, and the adsorption is only on single layer or monolayer adsorption, which means if we have adsorbent like this, so the adsorbate only will be present on the top layer or as only on one layer. So it won't be happening in multiple layers. Just a single layer of adsorbate will be covering the adsorbent. So for reversible and single layer, we can use Langmuir isotherm. And for multi-layer adsorption, we can use Freundlich adsorption isotherm. So we'll write the equation here. So the equation is 1 by q equals 1 by qm plus 1 by ka into qm into 1 by c. So here q is x by m. So x is the amount of mass of adsorbate and m is the amount of or mass of adsorbent. And qm is actually the maximum value of q. And c is the pollutant concentration. And then Freundlich equation. So again, x is the mass of adsorbate. M is mass of adsorbent. And Kf here, which is similar to Ka here, is the constant. So here it is the Freundlich capacity factor. And C is the equilibrium concentration of the adsorbate in solution. Okay, so in order to develop isotherms, we need to do batch studies. So batch studies involves taking a small amount of water or wastewater and adding some amount of adsorbent in it and observing how much of adsorbate is getting removed and at what time. And if we collect data, like for example, if we know how much concentration is going to be there after every unit of time in the solution, then we can get the value of CE. And once we get that, we can easily calculate how much of adsorbate is present in the uh, adsorbent, and then we can plot the equations. But in case we go for industrial applications, we need to do continuous study in the column. So unlike batch, a column, continuous study will is done using a column. So a packed column will be there. So it will be packed with adsorbent, and then there will be continuous inflow and outflow. So these studies are also done. So for absorption, the breakthrough point is defined as the point where 5% of the initial concentration of the adsorbate is coming out in the solution. So why we take 5% is ideally when we pass a solution or a wastewater through adsorption column, uh, we uh, we should ideally have 100% adsorption. But in case all the pores are completely blocked with the adsorbate, and there are no more pores left, what happens is the wastewater will just get bypassed, the pollutant will get bypassed, and it will just come out of the column unabsorbed. So if the concentration of that pollutant reaches 5% of the inlet concentration, then we call that time as breakthrough point. So, for example, if it has been 10 hours since the freshly prepared column was used, and after 10 hours, we are observing 5% of the observing that the outlet concentration is reaching 5% of the inlet concentration, then that point of time, that is 10 hours, is taken as the breakthrough point. And then we have exhaustion point. So here the effluent concentration equals 90 to 95% of the initial concentration. So what this means here is that 90 to 95% of the adsorbate is not getting absorbed. It is just coming out of the column. So at that point, we call it as exhaustion point. So the column has reached its exhaustion. At breakthrough, it is slightly starting, but at exhaustion, it is assumed that the column is exhausted and needs to be regenerated. And we also have total exhaustion. So total exhaustion means the column is completely exhausted. There are no pores left. And when that happens, the outlet concentration or C the outlet concentration becomes equal to inlet concentration, meaning there is no adsorption taking place, so there is no concentration reduction. Whatever concentration was there in the inlet is just coming out directly without getting absorbed. So in that case, C by C naught will be equal to 1. And if C by C naught is 0, what does it mean? What does it mean if C by C naught equals to 0? Outlet concentration and inlet concentration. Outlet concentration by inlet concentration is 0. What should it mean? It means the outlet concentration is very less compared to the inlet concentration, meaning that the adsorbate is still absorbable, that the column is not exhausted and breakthrough has not reached, and it is like behaving like a fresh column. So whatever adsorbate we put, it is completely getting adsorbed. And if C by C naught is less than 1, what will it mean? Okay, what does it mean if it is greater than 1? If it is less than 1, it means whatever adsorbent is there, it is getting adsorbed. But if it is greater than 1, it means the adsorbate is not getting adsorbed and it is easily coming out. Then we have something called the adsorbent usage rate. So this is the amount of adsorbent used per unit volume of wastewater. So basically, if you have 1 liter of wastewater and we are using 10 grams of adsorbent, then the adsorbent usage rate will be 10 grams per liter. So it's like that. And then there is empty bed contact time. So what empty bed contact time means is the amount of time that the adsorbate will remain in contact with the adsorbent. So this time is given as a ratio between the volume of adsorbent bed divided by the flow rate. So, and then we have the specific throughput time, throughput volume. So this is nothing but the volume of water treated per gram of adsorbent. So now if we have 1 gram of activated carbon and it can treat maybe 100 ml of water or wastewater. So then 100 ml by 1 gram becomes your specific throughput volume. So this can also be written as 0.1 liters divided by 1 gram, or can be represented as 0.1 gram per liter. So generally when we do adsorption, we use 2 columns. So one column is for service and another column is for standby or regeneration. because if only one column is used, then if that column is exhausted and it has to be regenerated, then we cannot treat the water, right? So in order to prevent this situation, we will have two columns, one for treating and another as standby, so that when the first column is needs to be regenerated, the second column can be used. Okay, so do you have any questions from this class or from any of the lectures that you watched? Yes, ion exchange is used in industrial wastewater treatment. Like how we saw, it is used for removing ammonia and ammonium nitrate, and it is also used for removing hardness in water. So, shall we solve a numerical problem? Okay. So, this is based on adsorption. So, I'm going to give you a set of data and I want you to plot on Excel. If you have Excel, do plot it and tell me. Otherwise, you can do it later and tell me in the next class. Okay, so this problem is about adsorption. They are doing adsorption multiple times. So each run means run one means the first time, run two means second time, and so on. And in the first adsorption, in the first cycle of adsorption, the inlet concentration is 5. So 5 is in maybe you can assume that to be in milligram per liter, and 5 milligram per liter is the inlet adsorbate concentration, and the outlet adsorbate concentration is 1.2, and again this is in milligrams per liter. And QE is what we saw here. Okay, QE is the ratio of the mass of adsorbate in the solution to the mass of mass of adsorbate on the adsorbent divided by the mass of adsorbent. So QE is nothing but, I'll write down here, XE by N. So XE is the mass of adsorbate on the adsorbent. So this is basically whatever is C is the amount which is coming out. So QE is the amount that is retained on the adsorbent divided by mass of adsorbent. Now you have to plot the, you have to find find the Freundlich, you have to plot it. So you have to plot the Freundlich adsorption isotherm using this data. So how will you do it? So what is required here? This is the Freundlich adsorption isotherm. So I'll write it down again. Log x by n equals log kf plus 1 by n log ce. So now what all do you have? You have x by m, which is qe, and then you also have ce. But in the equation, they have asked for log x by m and log ce. So you have to find the log of both. So log qe and log ce. So can you find the log of these two values and tell me? What is log 1.2? What is log 1.2? Okay, if you're not interested, then maybe you can solve it and tell me in the next class.
Okay, ma'am.
Yeah. And once you find the log of QE and log of CE, you will get a set of values, and you have to make a plot on Excel. So your x-axis will be log CE and your y-axis will be log QE. So because this is an equation of the form y equals to c plus mx, so here y is log x by m and x is log ce. So once you make a plot, you have to find the slope and the intercept. So this is the intercept and m is the slope. So you have to make a plot and find out the intercept and the slope. So intercept is log kf and slope is 1 by m. Okay, so if you have any questions, let me know.
Madam, selectivity coefficient is there, madam.
Yes.
How to find out the selectivity coefficient of two anions, ma'am?
Okay, I'll get back to you later on that.
Okay, ma'am.
Okay, any other questions?
No, ma'am.
Okay, if there are no questions, then I'll end the session. Okay, thank you all for joining, and see you in the next class. And solve the question and come. So if you're not able to solve, we'll discuss it.